Now, let's say we migrated our data to the database. And now what we want to do, we want to have the secure access for the data. And this is always a difficult task. And it gives like lots of temperature around the teams, like how do you want to like secure the data, how do you want to access that. But now it's going to be a very interesting topic on the next speech, which just came on the Mongo 6.0 release, which this is still in the preview. But what we hear already like around from the customer, this is a hot topic, definitely. And Queryable Encryption covered by Bart Polot, who's actually super enthusiastic, like security solutions architect from our team in Munich, is going to cover this topic for you. So welcome, Bart. Stage is yours.
Thank you very much. Thank you, everyone. So, as mentioned, my name is Bart Polot, solutions architect in MongoDB. And I'm very passionate, really, about security. A little background about me. Maybe some of you know the concept of the Erdos number or Kevin Bacon number, the degrees of separation. I worked in secure communications and encrypted communications a little bit. So I have some very interesting numbers. My Julian Assange number is 2. My Edward Snowden number is 2. My Bin Laden number is 4. And my Erdos number is just 5. So it's not that high, not that low. All right, so if you have the kind of guys that go after your data, as Julian Assange, Snowden, all these people, you really need to protect your data well. Just putting it in a server in the cloud, it's probably not enough. So for those use cases, like health data, financial data, we have developed Queryable Encryption. So what are we going to talk about today? This is our agenda. It's a little bit of a mouthful, so I simplified it. We're going to debate why, about what it is, how you can use it, how it's implemented, the comparison with client-side level encryption, so the one before, how you can use it, and what is next. All right, so the first one is going to be the why. Why do we need this? So I hope most of you saw Sahir's presentation that data is usually very well protected in flight. So TLS has had its bumps, but it's usually aware and understood technology. It's quite secure if you use the correct versions, of course. But the data then is decrypted in the server. So then we have encryption at rest, right? So it is encrypted on the rest, but then it is decrypted as soon as the database starts. Is anybody here has a database that it's not running? I don't see a lot of hands up. So usually the database is running, so the encryption at rest is only useful for against certain attacks. So when our application is running, when the database is running, the data in the memory is unprotected, is decrypted, is available because the database has to use it. And there's very few practical solutions for this problem, to protect the data as it is living in the database. So who can access this data? First of all, your DBAs, administrators, privileged users, somebody with physical access to the machine. There's very cool attacks in which you get compressed gas, you freeze the RAM, you extract it, you put it in another machine, and you read it. NSA, kind of James Bond attacks, but they are practical. It's been demonstrated that those are possible. Just process inspection, or generally cloud providers. So your administrator at Amazon, sure, everything is audited, but at the end, it's a trust problem. It's a pinky promise that the cloud provider promises with lawyers that they are not going to take a look at your data. That includes MongoDB as well as the company. If you have a server in Atlas, we promise, we guarantee with a whole legal framework that we are not going to look at the data, but you still have to trust us. So first of all, that is why we build client-side field-level encryption. So you can think of it as the first generation of the encryption solution. And now we have queryable encryption. So what it is, usually you have two options when you have data encrypted from the application or sensitive data in the database. You either don't encrypt it from the client side, and you just store it as it is. You trust the network and the encryption at rest. So you have very fast querying, but the data is not secure in use. So all this list of attacks are possible. Otherwise, you can encrypt it, and it is very secure, but then the server cannot reason about it. So every time that you want to do a query on these encrypted fields, basically you have to download the whole database or the whole table, the whole collection, and then on the client side filter because you have the key through what you want. So we developed Queryable Encryption to get the best of both worlds. So you have the data encrypted, it is protected on the database server, but it's queryable efficiently, so you can extract it with little delay and little network traffic, little overhead. So how it works is you have a client with an authenticated login that can talk to the database and a key server. So first of all, the client sends a query. For example, I want to take a look at all the purchases done by this credit card number. So we have our billing collection, and we have our credit card number. So we send that. But of course, we want to protect that. We want to be PCI compliant. We want to not be on the news. OK, so the driver itself contacts the key server and gets the key for that particular field in that particular document. What happens next is this query that was in clear text. We had the credit card number right there. It is encrypted, and it is sent encrypted to the server. So the application sent it in clear text, no changes to the application. The driver sent the request as an encrypted one. So that reaches the server. The server takes a look at all the contents that it has. Some magic happens, which we'll take a look later, and says, OK, all these records actually match that query. You can see that they are not exactly the same. The fields in orange are all different. But the server knows that in this case, those are the corresponding results for that encrypted query without knowing the credit card number. So we see that the pair is in clear text, but all the other fields are still encrypted. So this encrypted result set goes to the MongoDB driver. We still have the key that we contacted in step 2, so we can decrypt everything and send it to the application. So when it comes to the application, it's actually all in clear text. The application doesn't know that this happened, more or less. So on connection, there is some changes, but once the application is connected and the driver is initialized, everything is transparent for the application itself. All right, so this is what we wanted, right? We have very efficient querying. We have protection. All right. What are the key advantages? You don't need to be an crypto expert, so everything is implemented for you. You don't need to change your code. Again, the application is almost unaware that all of this is happening between the driver and the database server, and you can query your data securely. So all the data that is encrypted, you can still query. You can, of course, query the non-encrypted data, but the encrypted data as well. So how can you use this? What are the use cases? For instance, in financial services, you're doing fraud detection, and you need to check some ranges of dates or euro amount transactions. Like, give me all of the transactions that were between 9,000 and 10,000 euros, because it could be a fraud that they are going to fly into the radar of 10,000 euros. Or in human resources, retail, the last 4 digits of their ID number, of their credit card number, something like this. Healthcare. In healthcare, you probably have to protect most of the data. But still, you want to search. Like, you don't remember how to spell the patient's name. You just input the first few characters of their name and want to take a look at the database contents based on that. So if you want to have one slide for your manager or for your developers, here is a short recap of all the high-level advantages that it has. So rich querying of encrypted data, end-to-end, fully randomized encryption, so no statistical analysis. So it's standards-based cryptography. We haven't invented any new crypto algorithms. We will see the details later. It's all based on AES. Strong controls for privacy, faster app development. We're all about development productivity, and to reduce the risk. All right, so this, Sahir talked about it. This is not something that we just made out of the blue. This is not a hobby project. This is something that we've been doing for at least 3 years, at least publicly. So in 2019, we started with client-side level encryption. We hired very smart, very educated PhD researchers that have been working on structured encryption at least since 2011. That was the date of the first paper published. And we have been implementing features, and we'll be adding features in the future. So today, we have identity. We're going to introduce range, prefix, suffix, substring, and new privacy-enhanced features in the future. Detailed list will come at the end of the presentation. So what is available right now? If you go right now to our website, you can take a look at the crypto framework. So all this code is open source. You can take a look at it. The possibility of doing equality, and Compass is already fully aware of this. So if you're using Compass, you can select whether you want to connect with the key or without the key to check how your data looks encrypted or how your data looks decrypted. So all of that is available right now in the 6.0 public preview. And why is it a public preview? Well, there's certain things that we say we might make breaking changes. So that is not recommended for production. We're not guaranteed that we're going to be breaking changes, but we reserve the right to do that. So that's why we don't recommend to use it in production. If you use it in production, bad things could happen. So additional query types. Right now we have identity. We're going to come up with range in December, prefix, suffix, substring later in 2023. And now let's take a peek under the hood. Let's see how this works internally. Any crypto freaks in the, or sorry, enthusiasts in the audience? Some? All right, cool, cool. So let's take a peek under the hood. This is under the hood. No, I'm kidding. This is just my son. I practiced the presentation on him. Let's really peek under the hood. So we are in the classic stat. We can pick under the hood of many things today. One of them will be queryable encryption. So let's start talking about security model. So what kind of attacks is this designed to resist? So this is multi-snapshot secure. That means that an adversary, like a cloud provider, can take multiple snapshots of the database at different points in the future and have access to absolutely everything on the database. So not only the disk, but also the memory and even the internal CPU state. We allow that because a cloud provider, for instance, the NSA or CIA, do have that access. Then we have the formal security guarantees. So the encrypted fields are verifiably CCA secure. So what does CCA mean? It is chosen ciphertext attack. This is the attack, for example, that broke SSL so badly that they had to change the name to TLS. So this is an attack that it was practical. It has been implemented. So we designed it so it's resistant to this kind of attack. That the ciphertext don't reveal information about plain text beyond, of course, the size. So this includes, for example, frequency analysis. Right? So it is randomized encryption, something that was not possible with client-side level encryption. And the encrypted indexes, so we have the fields in the document, and then the indexes are secure against multi-snapshots, adaptive multi-snapshots. So again, CCA, the A stands for adaptive, in which the attacker can adapt their attack based on what he has seen before. All right, so there's two parts here, the boring part and the exciting part. The boring part is all the standard crypto that we're using. The exciting part is how we're using it. So the boring part is we're using AES, we're using SHA-256, so all standard measures, AES in CTR mode. We have a key that is composed of 3 elements, one for AES, one for HMAC, and one key for encrypted search operation. So again, this all happens in the driver, which is part of the application. Nothing of this, no key or anything like that lands on the server. Then the exciting part. So the exciting part, as we mentioned before, it's based on structured encryption. It's a novel concept, developed 2011, in which we do encrypted multi-maps, and for that we need pseudo-random function evaluation, PRF. So in order to have fast PRFs, what we use are keyed HMACs. So we know that HMACs are fast, are secure, so that is what we use for our pseudo-random. So pseudo-random means that it looks random without being random, really. So you can do the search. And these HMACs are fed by secret keys. So we have that key as part of our 96-bit key that I showed before. So it all is not analyzable from the server side. There is a number of protections around this for attacks like denial of service. So denial of service or just unreliability of clients dropping, writes not completing. So this structure it could be fragile if you don't design around this. So that is something that we took care of the practical details of the implementation. All right, so that was a short peek under the hood. If you want more details, we have a number of papers. If you're left with this phase after seeing all these acronyms, don't worry, we will have something more interesting now. So the more interesting thing is a comparison with client-side file-level encryption. So now, as of this moment, we have two client-side encryption modes for MongoDB. So what are the similarities? What are the differences? First of all, this is not a direct replacement. Client-side file-level encryption is not being deprecated. Both are supported. Workloads, which you already have on client-side file-level encryption, should stay. And queryable encryption is for net new workloads. That is after the preview, of course. So once it's in general availability. Similarities. First of all, both are secure. Duh, right, obvious. They should be secure. Both offer queryable and non-queryable options. So if you want your data to be non-queryable, well, that is a little bit of overhead that you save. You don't need to create the index. You still can retrieve the data. Both are based on AES. Small difference, CSFLE uses CBC mode, Queryable Encryption uses CTR mode, small details. Both have common key management features. Both encrypt the data on the database side as binary. So the only thing that the database is just a binary field. So not even the data type is leaked. And both can use, as of a couple of weeks ago, a shared library. So before, client-side file-level encryption required a daemon, which made it a little bit complicated to deploy in serverless environments, in containers. Now, both can use a shared library. So those are the similarities. What are the differences? So the differences is, first of all, the server-side support. With client-side file-level encryption, the server-side support was barely anything. All of the work was done on the client. The server didn't need to do anything because we didn't have this queryable part. With queryable encryption, the server part is integral to the whole schema. It's integral to the whole system. The queryability. With client-side file-level encryption, we had just equality. With queryable encryption, as the name says, we have more. We have range, prefix, suffix, substring. The frequency leakage, if we have health data and we encrypt, for instance, blood type, we know that certain blood types are more frequent than others. So even if we look at the encrypted data, with client-side level encryption, if you use deterministic encryption, we could just do a frequency analysis and based on the encrypted values, determine which blood time a certain person had without needing ever to decrypt the data. That is not possible with queryable encryption because it is randomized encryption. The key usage, with client-side level encryption, we have one key per field, per document, per collection. It is flexible. With queryable encryption, we need to have one per field based on how the indexing works. And client-side level encryption didn't have any additional data, almost. There is some metadata in the field itself. But with queryable encryption, we have one extra field in each document and 3 additional collections for the indexing. So we're working on hiding those so nobody modifies those. It is very important not to modify this because if you do, well, bad things will happen. So what are the trade-offs? In which situation should you use which technology? So if you have a lot of inserts, client-side level encryption is faster because we don't have to build these complex indexes. If you're doing finds based on equality, both are fast, both are good options. If you want to do other more complex kinds of queries, well, then we are out of luck with client-side level encryption. You will need to use queryable encryption. The storage overhead with client-side level encryption is minimal. With queryable encryption, as we saw, one extra collection, one extra field, three extra collections. And finally, the frequency leakage, which is a potential issue with client-side level encryption, not an issue with queryable encryption. All right, so how does this compare to other solutions? This is not the first solution on the market that tries to address this problem. So on the top, we have queryable encryption using this structure encryption concept. So it is very, very well optimized for real-time database operations, for transactional workloads. So it doesn't have or doesn't need any support from the hardware. It can run on any hardware. Of course, if the hardware offers AES acceleration, it will be much faster. On the client side, not on the server side. The server side doesn't do any AES. And it is optimized for sublinear searching. Then we have 2 other technologies that have been quite popular, or at least there's a lot of research and attempts from different entities. First of all, we have homomorphic encryption. So for those that are unaware of what it is, homomorphic encryption is an encryption methodology in which you can do operations on the data while it's encrypted, give this encrypted result to someone with the key, and they can decrypt the data and then retrieve the result. You can think of it as like calculating the average of a field in a collection, or calculating a sum. You just add all the data as it is encrypted. You just give that encrypted value to the client with the key, and they can read it. So this kind of encryption allows you to do a little bit different queries, more analytical queries on the data. However, it is not offered on any major general-purpose database. The queries usually are quite slow as the data grows, so there are certain limitations. It is very heavy on the hardware, so you can imagine that this encryption is not as fast as AES. Usually, RSA is kind of homomorphic in certain aspects, so it is as expensive to do as asymmetric crypto. So if you have ever done benchmarking on asymmetric crypto, you know that with AES you can do gigabytes per second. With RSA, you can do thousands of operations a second on modern hardware. So kilobytes or maybe megabytes a second. Then we have secure enclaves. So secure enclaves, you can think of like your Intel SGX, like your Apple T2 chips, all those things. So in consumer devices, they have been quite popular, but for cloud environments, they require specialized hardware. which has yet to prove secure. So Intel SGX, for instance, they are very brave trying to do that, but every version of it, every generation has been attacked already. So they are working on it. It is not yet there. And still, the cloud provider has all the keys. So the hardware provider guarantees that they cannot access the data, but still they have the data and the keys. So it is, again, a kind of a trust issue. This is a pinky promise that that it's not possible to access your data. And finally, those enclaves are not as powerful as general-purpose CPUs. So the security guarantees there. If you're Edward Snowden, if the NSA, if the CIA is after you, yeah, you have to think really about who you trust, right? So if you like what you see, you want to try it out, you want to play with it, how you can do it, what can you do as of today? First of all, the core crypto library, it's available. And it's available for Atlas, for on-prem, Enterprise Advanced, and for community. So we encourage peer review to see if there is any bugs. We have done professional peer review, audits of the code. And as I mentioned, all based on AES, SHA 256, standard crypto primitives. No black box here. That is the core library. If you want to use the automatic encryption, so just telling to the driver which fields you want to encrypt and letting the driver do all the heavy lifting for you, that is available in Atlas and Enterprise Advanced, just like client-side encryption was. We offer a crypt shared library for a number of programming languages. And this enables this encryption without any app changes other than the connection string or connection method to the database. If you want to download this, if you want to check it out, I have a QR code here that takes you directly to the downloads page. Google is your friend afterwards if you want also to check it out on your laptop. Be careful with it. As I mentioned, if you try to use it in production and we make any changes, not only it will kill you, it will hurt all the time you're dying. If you do any change on the metadata, it will hurt. You can lose your data, so be really careful what you're doing it, but have fun. I mean, it is really cool technology. So who can use it? You need a 6.0 server. We saw that you need support from the server side to use it, so you really need a 6.0 server. You need compatible drivers. So latest version of the drivers for a select number of languages. I hope that your preferred language is on that list. Node, so JavaScript, Java, Python, C#, Go, PHP, and Ruby. Those are all supported. And as I mentioned, for the automatic encryption, it is Atlas or Enterprise Advanced only. All right, a little bit of roadmap, what is coming soon. Enhancements to key management that we had in the timeline. So key rotation. So you can rotate the whole MongoDB key vault. Usually, if you do key rotation in a cloud provider, it's key versioning, really. The old version still is there, and the new version of the key is used for new data encryption keys. With this, we can rotate the whole wallet. So with one API call, you can rotate all the keys in your wallet, in your keyring. Another option that we are going to have soon is key migration. So this is changing the key from one provider to another without touching the data. So changing the key encryption key without touching the data encryption keys, or at least the data that is encrypted with those. So a single API call, I mean, it says now, but it is in the future, will migrate your keys from any cloud provider. So you start on AWS. Actually, GCP makes you better price. You can migrate. You start developing locally. You want to migrate your workload to Azure. Yeah, no problem. Any X and Y, any combination of key providers you can use. This is no impact to your application of your data. Everything is done with one API call. And finally, we have the custom key management. Certain workloads, certain industries require a higher level of guarantees to your data or to the keys. like generating the keys in an HSM, for instance. So this is something that was not possible until now. Now you can provide your own keys. So think of it as a little bit as bring your own key, again, all done with an API call. So that was my presentation. Again, please give your feedback. Please scan the QR code. If there are any questions, I will be happy to take them.
Thank you, Bart.